Tryptophan operon. Uh, it is a basic paradigm of looking at the fact that regulation of gene expression can happen after the transcription initiation when you have the RNA polymerase in the elongation step. Unlike lac operon, arabinose operon, and in fact even tryptophan operon, you have most of the regulation happening before the RNA polymerase starts transcription. But tryptophan operon also has another regulatory mechanism that is looking at possibility of regulation post transcription. So therefore, let us look at the learning outcomes of this session. The tryptophan operon that regulates the biosynthesis of tryptophan is able to regulate at the initiation step. So that we have already looked at is by using a aporepressor, and on binding to tryptophan, it will become a holorepressor, and that can go and bind to the operator region, thereby stopping the synthesis of tryptophan. But it also has a post-transcription initiation regulation, and that is during the elongation phase. This is what we are going to discuss in this session. Now, one regulation, therefore, that we already looked at was the on and off mechanism, while the second one is a modulating regulation in which the enzyme concentration varies with the concentration of the tryptophan. The tryptophan L, that is the L peptide, leader peptide gene, gives rise to a leader peptide, and it is when this peptide is being synthesized that there can be termination of transcription or the elongation can continue. So either of the two will happen. One is either the transcription will terminate immediately after the leader peptide is formed or when the leader peptide is being formed, or it can continue to elongate and go to transcribe all the structural genes of the tryptophan. Within the TRPL gene is present certain sequences that are called as attenuators. The word attenuators means weakening of a system. So we will look at how that happens, and which brings in the concept of what is called as anti-termination. Now, we all know that this is how the tryptophan operon is structured. So, we know that it has a promoter overlapping with an operator region, followed by the leader peptide gene, a small spacer, and then you have the structural genes. So, let us understand what is modulatory regulation by the tryptophan operon. So, if you have the aporepressor not as in the form of holorepressor, then what is going to happen is that you have the RNA polymerase coming and binding to the promoter and starting transcription. Now, as it starts transcription, the first gene to be transcribed is the gene for the leader peptide. So, therefore, the RNA polymerase will keep synthesizing, okay? But what has been observed is that before it is able to transcribe the structural genes, okay, it is falling off or it stops transcription, and you just have the leader peptide being formed. The remaining structural genes are not getting transcribed. So this is what is understood by premature termination of transcription, and the frequency of the premature termination of transcription is dependent on the concentration of the tryptophan. That is the key to leading to premature termination. So just like in case of the holorepressor being able to bind to the operator or not being able to bind to the operator is dependent on the tryptophan concentration, similarly the modulatory regulation system is also dependent on the concentration of tryptophan within the bacteria. So, and plus there is another thing, very important thing to be taken note of, and that is that this regulatory mechanism is possible because transcription and translation in prokaryotes are coupled. That is, they go on hand in hand. So therefore, let us now look at the attenuation. That is, what are the attenuator sequences doing? Okay, and attenuation, as I mentioned, is basically weakening of the system. So when you look at weakening of the system in case of tryptophan operon, you're looking at its ability to transcribe the structural genes becoming less or becoming weak. So let us look at the fact that it is between the start point of the transcription for the entire tryptophan operon, that is at this point, okay, where the mRNA begins to be formed, and the start point of the structural gene, the first structural gene, that is TRPE. This basic region is about 162 base pairs, and it comprises the TRPL gene. Now, within the sequence is present the attenuators that are responsible for the regulatory activity. So, these attenuators are either responsible for termination of transcription, or they're responsible for the anti-termination of this thing. When you say anti-termination, it means that it does not carry out premature transcription termination. It will allow the transcription to continue. Now, if the termination happens, then the transcript that is formed is only about 40 nucleotides in size, okay? And therefore, you can consider that it is ultimately a truncated mRNA that has been formed. And this 40 nucleotide long mRNA that is formed, from that one is able to get either a truncated leader peptide or the complete leader peptide as well. Now, let us understand what the attenuators do, or what are the attenuators. So within this, so now we are basically looking at only, so this is the promoter operator region, this is the TRPL gene, that is the leader peptide gene, the spacer, and this is the TRPE gene. So we are looking only at this region, which is about 162 base pair long. So within the 162 base pair long region is present 4 distinct sequences, okay, and these sequences, they are able to base pair with each other. That is because there is complementarity within them, and you would find that they are more or less inverted repeats. So because they are inverted repeats, they are able to basically join together or hydrogen bond with each other to form stem loop structures, that is the secondary structures in the RNA. So when the RNA polymerase binds to the promoter region and starts the transcription, and as it starts the transcription and this gets transcribed, in the RNA also you will have 1, 2, 3, and 4, these 4 sequences. And we said that they are able to hydrogen bond with each other. So there are 2 possibilities of how they hydrogen bond to form the stem loop structure. The first possibility is that 1 and 2 hydrogen bond with each other, and 3 and 4 hydrogen bond with each other. And the second possibility is that 2 and 3 hydrogen bond with each other. Now, if 2 and 3 hydrogen bond with each other, 1 and 4 will never be in a hydrogen bonding, or they will not be able to form a stem loop structure. So therefore, when you have 1 and 2, okay, this seems to be a structure which is able to pause the process, okay. This is a structure which is, or it is a stem loop structure that is able to give a cue to the RNA polymerase that it can continue transcription. And this over here is a stem loop structure that is formed that gives the cue to the RNA polymerase to stop transcription. So basically what you have over here is what is called as the termination loop, and what you have over here is what is called as the anti-termination loop. So if this is formed, then you will not have transcription stopping, but if this is formed, then you will have transcription getting terminated. So the question very clearly is that you have these, you have these 3 stem loop structures possibly happening, but then one leads to termination and the other leads to anti-termination. How and when? So let us also look at the fact that when you are considering this 3, this is 3 and this is 4. So you can see that it has diet symmetry with a few nucleotides in between that do not have complementarity. So they become the part of the loop, and these two form the stem. because they are able to hydrogen bond. Now, interestingly, what has been observed that after the fourth attenuator sequence is present, a stretch of A is in the G, and so when the transcription happens, there is a stretch of U in the RNA that is formed. This is exactly similar to the intrinsic terminator sequence, and therefore this stem loop structure that has formed between 3 and 4 is basically a cue for termination for the RNA polymerase. So when you have the 3, 4 coming together to form the stem loop structure, and that stem loop structure is followed by the U's, then termination will happen. So therefore this is the cue for termination. Now, when you have the RNA polymerase bind to the promoter region and starting transcription, you will find that the transcript is being formed as the RNA pol moves forward. Now, as it moves forward, say you had 1 over here and you had 2 over here. So, when 1 and 2 have been transcribed, immediately that it is transcribed, you know that it can form a stem loop structure, because it is always known that when there is complementarity, there will tend to form a secondary structure, because that becomes thermodynamically more favorable. And so the moment 1 and 2 attenuator have been formed, you will find that the structure between 1 and 2 has been formed. At this instance, the RNA pol pauses a while, and then it continues again to synthesize. Now, as it has synthesized the 3 and the 4th attenuator sequence as well, you will find that the 3 and 4 will also complementarily bind to each other to form now the two stem loop structures, that is one between the 1 and 2 and the other between the 3 and 4. And we know that the one between 3 and 4 is the termination sequence. And what is going to be synthesized now is poly U. So therefore, once that has happened, the RNA pol falls off, because it is no longer a stable structure because of the formation of this secondary loop structure. So therefore, you can see that mRNA of the entire tryptophan operon is formed only until this spacer region. The tryptophan E gene is not being transcribed because the RNA pol has fallen off. And why has it fallen off? Because of the presence of the terminator stem loop structure. So the question again, let us ask, is when does termination happen and when does anti-termination happen? And this is dependent on the concentration of tryptophan. So let us come back to understanding that if you have tryptophan levels in the system different, what happens? So let us look at the fact that RNA pol has bound to the promoter region as has begun the transcription. So you can see that the RNA pol has begun transcribing the first attenuator sequence. Okay, as it continues to move, so in the meantime, because in the prokaryotes transcription and translation are coupled, that is that they are carried out hand in hand, you will find at the end of the transcript you already have the ribosome coming and assembling and trying to form the polypeptide. So now you have the RNA pol transcribing at one hand, and you have the ribosome translating the transcript that this RNA pol is forming. So let us move ahead. And before we move ahead, please understand the leader peptide, okay, is only about 14 amino acids long. And interestingly, the 10th and the 11th amino acid residue of this leader peptide both are tryptophan. So within the tryptophan leader gene, you have two codons for tryptophan adjacent to each other. And that is extremely strategic. So we will understand why it is extremely strategic. So let us again look at the fact that you have now the RNA pol transcribing the second attenuator. You can see it has moved forward, and the ribosome has reached on the transcript the region where the first attenuator sequence is present. So basically we are looking at the fact that the ribosome is positioned on the first attenuator sequence on the transcript. Okay. Now what we understand is that the first attenuator sequence is coinciding with the end of the tryptophan leader gene, and you know that if it is giving rise to 14 amino acids, then the 10th and the 11th amino acid codon, that is tryptophan codons, will be positioned exactly at where the attenuator sequence is. So basically, let us look at the fact that the attenuator sequence has within it the codons for the tryptophan. Okay. Now, therefore, if the cell has enough amount of tryptophan, there will be sufficient amount of charged tRNA for tryptophan. So the ribosome just has to incorporate the charged tryptophan tRNA and continue synthesis. So in a scenario where you have enough tryptophan present in the cell, the ribosome does not have to halt at any position. It will just simply continue to translate. So therefore, what is going to happen is that the transcription is also continued, the translation is also continued. So you can see that one has already been passed by the ribosome, and now it is at the second position that you have the ribosome. Now it's not going to move forward any longer, it is actually going to fall off, because at this point you have what is called as a stop codon for TRPL, right? So therefore this ribosome basically actually has to fall off. Okay, and you will find that it does fall off, giving rise to the leader peptide. Okay, but you can see now that as the RNA pol moves forward, the third has been transcribed. So you have the third sequence over here. The fourth is being transcribed, but the 1 and 2, because they are free, you see the ribosome has fallen off. So the 1 and 2 will form the secondary stem loop structure already. And as you have the RNA pol moving forward, you will also have the third, fourth loop formed, and you will have the RNA pol falling off, because this is the termination stem loop structure. So ultimately what we understand is that tryptophan being enough, the ribosome move fast translating the leader peptide, as there are sufficiently charged tRNA. And so it did not wait on any of the sequences, it just continued. So when it was on 1, 1 was not able to bind to 2. Okay, but when the ribosome moved from 1 to 2, 2 was not available to bind to 3. Correct? Now when it falls off from here, 3 is available. Okay, or 3 is being still synthesized by the RNA polymerase. So 1 and 2 are free, and hence they will immediately form the first stem loop structure. Then the RNA pol moves forward, and the 3 and 4 bind together to form the termination stem loop structure. And that is how, in presence of high levels of tryptophan, the RNA polymerase stops synthesis, and you only have a truncated mRNA being formed with just the leader peptide being formed. So that is what is premature termination of transcription, and that is also what we understand by regulation of transcription. So post the transcription, you have a regulation that says that transcription should stop, and transcription has stopped. And that is being basically controlled by the levels of tryptophan itself in the form of the charged tRNA for tryptophan. Okay, now let us look at the other scenario. Suppose you have less or no tryptophan present in the cell. Then what is going to happen? When you have the RNA polymerase transcribing the first attenuator sequence, okay, the ribosome has already come and bound and started synthesizing the polypeptide. As it reaches the second sequence and the ribosome reaches the first attenuator sequence within the transcript, as we know, there are two tryptophan codons that are present in this region. In the scenario where you have no tryptophan or very negligible tryptophan, you will not have charged tRNA for tryptophan. So therefore, the ribosome will have to wait for a charged tryptophan tRNA. So what effectively happens is that the ribosome stalls at this position, and this position is the sequence 1. So therefore, you will find that the ribosome is paused or is halted at the sequence number 1 on the transcript. But that does not stop the RNA polymerase from transcribing. So therefore, you basically have the RNA polymerase moving forward, But you can see the second sequence has been already transcribed, but the but the ribosome is still at the sequence 1 because it is still awaiting the charged tRNA. Okay, so therefore what is going to happen, and we just said there are negligible amounts, so therefore you would have very less charged tRNA. So charged tRNA would come to the ribosome, but the whole process is delayed because there are very less charged tRNA, and the ribosome has to wait for the charged tRNA to be incorporated at its A site. So with this, therefore, what is going to still happen is that when you have the ribosome still at the sequence 1, the RNA pol has moved forward, has synthesized the sequence 2, has transcribed the sequence 2, transcribed the sequence 3, and is now transcribing the sequence 4. But because 2 and 3 are now free, they will immediately form this stem loop structure. So therefore, what is the case in point? The case in point is that if 2 and 3 sequence form the same stem loop structure, then 1 cannot be in a stem loop structure and neither can 4 be in a stem loop structure. And we know that this stem loop structure is for anti-termination. So what is the cue to the RNA polymerase is that since the termination stem loop has not been formed, the RNA pol can continue to synthesize, and therefore RNA pol will continue to synthesize. Ribosome will take its time to continue translation because it waits for the charged tRNA, okay? And then you would have basically elongation of the entire system happening. So you can see that when tryptophan is low, you have the anti-termination stem loop being formed, and when tryptophan is high, you have the termination stem loop being formed. So that is how the the tryptophan operon is weakened by the process of attenuation, which ensures that if tryptophan is less, then the transcription will continue. But if tryptophan is greater, then transcription can be terminated. So that is what is attenuation or regulation at the post-transcription initiation level. So now therefore look at the conclusions. The modulatory regulatory mechanism of repressing biosynthesis of tryptophan is a very strategic mechanism, and this is possible due to the transcription being coupled to translation. The leader sequence and the spacer before the structural genes has 4 sequences that are called as attenuator, and they can hydrogen bond or base pair with each other. But the catch is that if a ribosome is present on one of the 4 sequences, then base pairing is not possible with the sequence to which the ribosome is bound. When tryptophan is absent or negligible, then due to ribosome stalling at attenuator 1, attenuator 2 binds to attenuator 3, and this base pairing is anti-termination. But when tryptophan is high, the ribosome does not stall and keeps pace with the RNA polymerase, thereby base pairing between attenuator 1 and attenuator 2 happens, and that ensures that the 3 and 4 stem loop structure is formed, which is similar to intrinsic terminator and therefore leads to termination of transcription. The RNA pol becomes unstable because of the conformational change and it falls off the DNA, stopping transcription. Thus, tryptophan operon's attenuation regulation is based on the signal of amino acyl tRNAs, the availability of the tryptophan tRNAs, okay? And the sensory part is the ribosome's ability to incorporate tryptophan in the leader peptide. This represses the operon by about 10 to 12 folds, and all these are post-transcription initiation. Thank you.